Okay, welcome everybody. We'll start in just a couple of minutes. Okay, I think we should get going. My name is Charles Scammy. I'm a professor at the University of Illinois, and I'd like to welcome all of you and thank you for coming to today's webinar, which is on VLBI polarimetry techniques, and this is webinar 1. So today's session is the third in our new series on Event Horizon Telescope data analysis techniques. And you can view the previous webinars on our PIRE YouTube channel, or sorry, on the PIRE YouTube channel. And I think Rosie is going to put the links for that into the chat. So if you're interested in future webinars, then please go see the topics, dates, and registration links at the PIRE website. And I do want to mention one additional thing that's going on this week. So Matt Turk from University of Illinois is going to be leading a workshop on YT, the use of YT for data analysis and visualization. And that will be happening this Friday, starting at 15 UT, so 15 to 17 UT. It's a 2-hour workshop. All right, so today's webinar is going to take exactly 1 hour, including the time for questions. And Iván has kindly agreed to stay on at the end to answer questions if there are any that can't be answered during the hour. So if you do have questions during Iván's presentation, then please post them to the Q&A. And if they look like they're easy to address, I'll forward them verbally to Iván during the talk. So our facilitator for today's webinar is Iván Martí-Vidal. He's a radio astronomer. He is an expert in interferometry and polarimetry. He's one of the leading workers in polarimetry in the Event Horizon Telescope collaboration. He's worked on a number of different fields, including supernova explosions, stellar atmospheres, and relativistic jets in active galactic nuclei. And he's the developer of advanced calibration algorithms that are fundamental components of high-impact VLBI projects, including the Event Horizon Telescope. And again, he's an active member of the ipht collaboration, and he's one of the coordinators of our polarimetry working group. So without further ado, Iván, please go ahead.
Thank you very much, and thank you for the invitation to give this seminar in the PIRE. It's a pleasure for me. Okay, so let's start. Yeah, every time I'm starting a talk or a seminar about polarimetry or polarization, I always like to remember a true story that happened to me at Amsterdam airport. Okay, it was a day I was running. Okay, because the flight was going soon. Okay, I was looking for the departure gate, and I couldn't find it because all the screens were turned off. Okay, I was looking at the screens of the gate departures. I couldn't find anything. And I was desperated, okay? I was running short in time. until I realized that there were several people staring at these screens, okay, which were turned off. I'm wondering myself, what is happening here? What are these people looking at? Until I realized that I was wearing my polarization sunglasses, okay? And as soon as I took my sunglasses off, then the truth came, yeah. The truth, ladies and gentlemen, is that, as you can see here, polarized light can carry a lot of interesting information, isn't it? That was a very nice truth that does not only hold in airports, it also holds in the universe, okay? Polarized light can carry a lot of interesting information, okay? If you see the universe in polarized glasses, you can have a lot of interesting information related to, for instance, just to name a few, star-forming regions, evolved stars, and our favorite monsters, black holes, okay, and relativistic jets from black holes. So if you study the universe in polarization, I'm pretty sure you will have a lot of fun, okay? There is a lot to discover. So in this seminar, well, I'm going to split it in 3 parts, okay? First, we will get familiar with some basics of polarimetry. I'm pretty sure all of you, or most of you, will be already familiar with this, but I think it's good to check this to test that, well, to check that we are on the same page. Then I will talk about processes that originate polarization in the universe, okay, especially the role of magnetic fields. We'll talk about, yeah, from dust polarization to AGN jets, okay. It will be very brief, okay. I will not go too deep into these details. And then we will learn about how polarization is measured in radio astronomy, okay, which is, I think, the key of this seminar, okay, the technique of interferometric polarimetry. Okay, I will briefly talk about the measurement equation, which is the very basic thing that we need when we do polarimetry with VLBI. And then we'll just describe very, very briefly some calibration algorithms that we use in VLBI. Okay, so let's start from the beginning, okay? The origin of polarization. Okay, so as you know, electromagnetic waves, or the light rays, basically are made of the time evolution of the electric and magnetic fields, electromagnetic fields. Okay, these are not scalar waves as sound. Okay, in the case of sound, you can basically describe the wave by wavelength and frequency. But when you have a vector quantity being disturbed, being oscillating, when the quantity is vector-like, you also have another kind of information, the directionality of the oscillations, okay? Well, we also know as polarization, okay? So electromagnetic waves have all things that the scalar waves have, but also directionality of the oscillations, okay? What we call polarization. From now on, when I talk about polarization, I will be specially referring to the orientation of the electric field, okay? Electric field, okay? So imagine that the magnetic field will always be perpendicular to the one that I'm always pointing at, okay? So we are going to discuss about the orientation of the electric field from now on, okay? And as you can see, these oscillations are perpendicular to the direction where the radiation is being propagated. So the energy is being transmitted in the direction of this green arrow here, which is what we call Poynting vector, okay? So don't forget about this, okay? So in ordinary light, okay, light rays are made of photons, okay, that have random electric field orientations. So in the end, when you have a natural light source, okay, what you usually have is a set of random, completely random orientations of the electric field that is being transmitted, or the electromagnetic field that is being transmitted, okay? So this is what I'm trying to show you here in the simulation, okay? Where these lines would represent the amplitude of the electric field, okay? That you can see is basically random, okay? But there are some cases, for instance, here you can see the case of the radiation finding a refraction surface with a Bragg angle, okay, where just because of the transmission of light across this media, okay, we can produce polarized radiation. Okay, so polarization can originate even from unpolarized light if the propagation medium selects, okay, certain orientations of the electric field. Okay, so in general, we can have two kinds of polarizations. Okay, two kinds of states of that describe the orientation of the electric field. Linear polarization on the one hand, which has a preferred direction of oscillations. This would be a representation of a linearly polarized electromagnetic wave, okay, propagating in this direction. And on the other hand, we have circular polarization, which is a bit more subtle to understand. Okay, in this case, the electric field rotates. Okay, rotates in the plane of the wave front. Okay, so rotates in the plane perpendicular to the pointing vector. Okay, rotates as the light ray propagates. Okay, and the period of rotation is equal to the period of the light wave. Okay, so in this case, you can have light rotating clockwise or rotating counterclockwise. Okay, so you have two kinds of circular polarization. In general, what you have in the end in nature is a combination. Okay, you can have a combination of different polarization states. You can have a little bit of linear in any direction and a little bit of circular at the same time. Okay, so you have a mixture. Okay, now the question is, if we have the most general state of light polarization, which is a mixture of linear plus circular, how many quantities do we need to fully characterize, to fully describe the polarization of light? Well, if you think a bit, we only need 4 quantities. Okay, first of all, we need to know how much polarized versus unpolarized light do we have. So what's the amount of polarized radiation? That's 1 degree of freedom. Okay, 1 quantity. Another one is how much circular polarization do we have, and what is the sense of rotation? Is clockwise or counterclockwise? And how much we have? That would be another quantity. Okay, the sign of that quantity would encode the sense of rotation. Okay. And then we also need to know what is the strength and the orientation, okay, of the linear polarization. This orientation is what we also call electric vector position angle, EVPA, okay, which we usually name as chi, okay, this chi Greek letter, okay. So there are 3 things. There are 4 quantities that have to be 4 degrees of freedom that we have to describe the polarization state. And one way to do it, it's not the only one, but one way to do it, which is the most used and famous one, is the Stokes parameters. Okay, so we have 4 degrees of freedom, and then we have 4 quantities that allow us to fully describe the polarization state of light. On the one hand, we have a Stokes I, which is the total intensity, that's unpolarized plus polarized. Okay, so it's everything here. Q and U, which encode information about the strength and the orientation of the linear polarization. You can think of this as if the strength and orientation are like the polar coordinates, okay, of the electric vector. Q and U would be a kind of, okay, kind of Cartesian representation, okay, kind of, but not exactly Cartesian, okay. I will tell you why in a few slides, okay. And finally, we have Stokes V, which is the amount of circular polarization, okay. It gives us the amount and the sense of the circular polarization. Why Q and U is not exactly the Cartesian representation of the strength and of orientation of EVPA? Well, the answer is this, okay, which is something that you have to be very aware of, okay? The EVPA, the electric vector position angle, in light polarization has the symmetry of pi rotation, okay? So that means that if you take a polarization state and you rotate it pi radians, you end up having exactly the same polarization state, okay? Half rotation is a full rotation in polarization, okay? Whereas in normal life, okay, when you use normal Cartesian to polar coordinate transformation, the symmetry is 2 pi, okay? So this subtlety here actually translates in a quite tricky way to define Q and U, as you will see in a couple of slides. Okay, there is a graphical way of visualizing Stokes parameters, which is called the Poincaré sphere. Poincaré sphere is actually more interesting and more important than it seems at the first glance, because in interferometric polarimetry, there are some quantities that are symmetric to certain rotations in Poincaré sphere. And knowing these things is always very interesting, okay, and can make your life a bit easier. So in the Poincaré sphere, the azimuth, each point on the sphere corresponds to a polarization state of light, okay? EVPA, so the electric vector position and the inclination of the linear polarization changes with azimuth angle, and the circular polarization, or the level of circular polarization, increases or decreases with latitude angle. So if you look in the website, or you look in books, optics books about the Poincaré sphere, you will see that there is some inconsistency in this animation here. So the origin of EVPAs, which is this direction, in most optic books correspond to the horizontal polarization states, whereas here I'm plotting it vertical. You see, the EVPA is rotating 90 degrees when you rotate 180 degrees in the Poincaré sphere. This is this 2 chi here, okay? The fact that the symmetry is pi radians, remember? But for us astronomers, 0 EVPA corresponds to vertical polarization, okay? This is very different from what you will see in many optics books, okay? So beware of this, okay? There's a different convention for us astronomers on the choose of the chi origin, okay? And regarding the circular polarization, as I have told you, so changes in latitude correspond to different levels of circular polarizations, okay? So you can have elliptical polarization when you are here, and when you are just at the pole, you don't have linear polarization and everything is circular. You have a perfect circle, okay? So this is the way we can compute the Stokes parameters, okay, from polarizing receivers, okay? And as you can see, this is not a mere Cartesian transform, okay? Look at how we do it. So if you want to compute the value of Q, what you have to do is to register the intensity of light in one direction and subtract the intensity of light in the perpendicular direction, okay? This gives you the subtraction of these two numbers gives you Q. And then if you rotate the whole thing 45 degrees and repeat the experiment, so register in this direction the intensity and remove the intensity registered in this direction, then you have the U. Okay, the reason why we do this and we don't do a mere Cartesian transformation is because of this pi symmetry in the EVPA. Okay, so this would be a perfect Cartesian to polar coordinate transformation if we wouldn't have this particular symmetry of EVPA. Okay, this is how we would compute the Stokes parameters. Okay, so once we know our friends, the Stokes parameters, let's talk about how they are produced in the universe. I will basically talk about two scenarios, okay? The universe is very rich for polarimetry. There are lots of different scenarios where you can have polarization, but I will just give you a couple of examples, okay? In one of them, we have dust polarization, okay, or polarization induced by dust, okay, which is caused by dust grains in space, okay? Imagine a proto-planetary disk, for instance, which is made of gas and dust. And imagine that you have dust particles that are not spherical, okay? They are elongated, okay? If this is the case, and if you have a magnetic field, then the excitation coming from the radiation, which is giving energy to the dust grains, will make them rotate. And since they are elongated and they have a given magnetic moment, okay, this energy will in the end be distributed as rotation energy with the rotation axis parallel to the magnetic field. Okay, this is like magic, what is happening in interplanetary and interstellar space with the dust. Okay, so depending on the observing frequency, these rotating dust particles will induce different polarizations. Okay, for the case of relatively long wavelengths or millimeter wavelengths, okay, not that long. Then we have thermal emission from dust, which would be aligned to the major axis of the dust grain. So this would be perpendicular to the magnetic field. Whereas if you have high frequency radiation, it will basically pass through, okay, and it will be absorbed in the long axis direction and will be let to come through in the minor axis direction. So you will have something which is parallel to the magnetic field, okay? So as you can see, polarimetry is a very powerful probe of dust properties, okay? The shape of the dust grains. Imagine we can measure this from the Earth, okay? And also the structure of the magnetic field in which the dust is immersed, okay? So a nice example, very nice one, I would have liked to provide more, but we don't have time, is this beautiful source that I'm pretty sure you will remember. This is the proto-planetary disk of HL Tauri, a very beautiful and famous image from the ALMA interferometer. And this is the same source seen in polarization at different wavelengths, okay? So as you can see, polarization allows us to probe the radial dependence of the dust properties and the structure of the magnetic field across and along the protoplanetary disk, okay? And allows us to study what's the role of magnetic field in the formation of planets, okay? That's amazing what we can do. Another source of polarization is synchrotron, okay, non-thermal emission. Okay, in the case we have very energetic relativistic electrons or relativistic plasma immersed in very powerful magnetic fields, what we have is this kind of radiation. Okay, so the electrons start to spin around the magnetic field lines due to the Lorentz force. And since they are being accelerated, they start to emit. Okay, and as you can see here, the orientation of the electric field of this emission caused by the acceleration of the electrons is perpendicular to the direction of the magnetic field. Okay, so in the end, if you have a region with relativistic plasma and strong magnetic fields that have a very well-ordered structure, so the magnetic fields are structured at large scales, then all the electrons will be emitting basically in the same direction. And you will have an overall polarization, okay, caused by this non-thermal emission. Okay, so you can probe the structure of magnetic fields with polarization of synchrotron emission. Well, one of the most prominent scenarios where you have this, where you have relativistic plasma immersed in strong magnetic fields, is the case of relativistic outflows, okay? Relativistic jets from supermassive black holes. As you can see here, these are real pictures, eh? This is not an artist impression. And this is also real data, okay? This is a movie made by José Luis Gómez a long time ago. As this is real data. You can see how the plasma travels along the jet, and you can see these lines here represent the magnetic field, okay? That would follow the jet direction, okay? It's wonderful what you can do. So magnetic fields that can be probed with the study of polarization of the synchrotron emission are closely related to the processes of accretion of matter in the black holes. Okay, so depending on how the magnetic fields are structured, for instance, we can have magnetically arrested disks. We can have a standard and normal evolution, which means the magnetic field has a weaker role in the accretion. Okay, depending on the magnetic field, you can have very different modes of matter accretion into the black hole, which in turn translates into different modes of the jet production. Okay, and you can also have different mechanisms of jet production. For instance, you could have jets produced by magnetocentrifugal forces from the innermost part of the accretion disk, the famous Blanford-Payne process, or you could have energy being extracted by the magnetic field and the plasma in the ergosphere of the black hole. And this energy would be extracted from the black hole itself. Okay, this is like, wow, it's a very exotic thing, isn't it? We can extract energy from the black hole via the action of magnetic fields and plasma in the ergosphere. This is what is called the Blanford magic. So as you can see, magnetic fields played a crucial role in the ejection of jets and the accretion in supermassive black holes. And of course, we need observations to probe all these models, okay, to test them with real data, okay? One of the examples, sorry, I don't have time to give you more examples, but I think this is the most beautiful one, is this work by Johnson et al. using an earlier version of the ipht with less antennas. And as you can see, what Johnson et al. Could do here was to actually infer information about the magnetic turbulence in the accretion flow of the galactic center of Sagittarius A star by studying interferometric observables in polarization. Okay, these are not real images. Okay, no, don't be confused. These are not images. This is a model, okay, based on the few visibilities that these authors could use. Actually, it would be fantastic to have an image in polarization of the neighborhood of an event horizon. Wouldn't it be fantastic? Because then we would be able to actually probe directly the modes of accretion and the role of magnetic fields in accretion. That would be fantastic to have. It's a pity we don't have it yet. Well, how do we measure polarization? Okay, this is the quid of the question. How do we obtain this beautiful science that I have just shown you? Okay, what we do in astronomy and in radio astronomy in particular is to basically decouple the radiation that comes from the sky into different polarization modes. Okay, and for that we use polarizers. Okay, which are devices that filter the orientation of the electric field in certain directions. Okay, you can see here a beautiful example how a polarizer, depending on its orientation, selects different orientations of the electric field that comes from the sky. Okay, so as radio wavelength, this is just a dipole. Okay, and in radio astronomy, what we have is actually not one dipole but two. Okay, we have two dipoles. Okay, two dipoles which register the radiation either in linear basis, so that means two orthogonal dipoles that would register coherently. This is the key of the equation. Coherently, the radiation coming from two different orthogonal polarization modes, vertical and horizontal, for instance, okay? And what do I mean by coherently? Because, well, what I mean is that the radio telescopes register this signal, keeping the relative phase between the two polarizers, okay? So we know the amplitude and the phase, okay, between the different dipoles that register the polarization in these two orthogonal modes. In VLBI, well, in radio astronomy, and in particular in VLBI, what we use is instead polarizers that register the circular polarization coming from the sky, okay? So they divide the radiation into orthogonal circular polarization modes instead of linear, okay? This is very useful. It has its advantages, okay? I'm not going to talk about these details, of course. But for you to know that in VLBI, we prefer to register the radiation in circular basis. Now, this is an example that shows you how can we reconstruct a full polarization state using just two coherent polarizers, okay? Remember, the key here is that they are coherent, okay? So in this case, the two polarizers of our radial telescope are these two lines, okay? And this is the radiation coming from the sky, okay? The pointing vector is pointing towards you, okay? So the wavefront is parallel to the screen. And this would represent, as you may know already, a state of linear polarization, okay, with a given EVPA, with a given orientation. And as you can see, if you have linear polarization, what your polarizers receive is basically a signal which is in phase, okay, in phase for the two polarizers. There's a phase offset of 0, okay, between the two polarizers. And different amplitudes would give you different EVPAs, basically. What happens if you have circular polarization? Then you have a phase between the two polarizers. Okay, as you can see here, I have added a phase of 90 degrees between the horizontal and the vertical polarizer. And this allows us to reconstruct circular polarization. Okay, if you add a phase offset of 270, you have the other sense of circular polarization, and any generic angle between the two polarizers will allow you to recover any generic polarization state, combination of linear plus circular, okay? So you see just only two polarizers allow you to reconstruct everything. What happens in VLBI when we have circular polarizers? Okay, in this case, what we do is to decouple the signal in two circular modes, okay, also coherently, okay? So in this case, when you have a signal that is linearly polarized, then the two circular polarizers receive the same amplitude, okay? Now, as you can see here, the phase between the two signals, okay, which is basically, yeah, this thing here, gives you the EVPA, gives you the orientation. And how would you reconstruct a generic light that would have circular plus linear? Well, just by receiving different amplitudes in each one of the polarizers. In this case, you have more amplitude rotating counterclockwise, and this gives you circular polarization rotating counterclockwise on top of linear polarization with a given EVPA that would be related to the phase between the polarizers. Okay, so you can do everything with two polarizers. Okay, now we know how to register polarization. Okay, we know that we need two polarizers observing coherently. Now the question is, what do we do with it? Okay, how do we couple this polarimetry with interferometry? Okay, which is the kind of technique that the ipht, Event Horizon Telescope, is using. So what we do is the following. Pay attention because these are the most important slides. Okay, so what we do is that we have, in a case of a simple interferometer of two elements, we have two antennas, okay, antenna A and antenna B. And each one of these two antennas registers two streams, okay, because we have two dipoles, two polarizers in each one of them. And we register it coherently, okay? So antenna A, for antenna A, we have two streams of data. The one coming from the right circular polarization, the other one coming from the left circular polarization, and the same thing for B. Okay, so we have four independent streams of data coming from these two antennas. Okay, what we do in interferometry, and you will see in the next slide why do we do it, okay, is to generate all these correlations. Okay, so all correlations between all possible combinations of polarizers and antennas. Okay, so on the one hand we have the parallel hands. Okay, the parallel hands cross correlations, which are called this way. Right for A and B, which means please take this data stream of right in antenna A and cross-correlate it with the R stream coming from antenna B, okay? Make this cross-correlation and call it visibility right, okay? For left, we do a similar thing, and a similar thing for right-left. We mix polarization channels here, and we mix polarization channels in the other way here. So in the end, what we have is four different cross-correlations between all different combinations of polarizers. Now the question is, Iván, why do we do this? What's the reason of doing this? Here comes the reason. What this computation allows us to do, this is basically what the ipht is doing to compute all different correlations between these data streams, is to recover the structure of the observed sources in full polarization. Okay, so this is done via the action of a very powerful equation called RIME, okay, radio interferometer measurement equation that I will show you in this slide. Okay, so here at left, we have what we measure, okay, this is what we measure, what we call the observables. And here at right, I show you what we want. Of course, what we want is the brightness distribution of all four Stokes parameters, which will allow us to reconstruct the full polarization state of light, okay? So what we do is the following. We arrange what we measure in what we call visibility matrix. Okay, so these 4 correlations that I told you about in the previous slide, we arrange them in a matrix form. Okay, right, left, right, left. Okay. On the other hand, what we do is to arrange the brightness distribution of Stokes parameters in another matrix. Okay, which is not the mere Stokes parameters, as you can see here. Each element is a funny combination of Stokes parameters. Okay, this brightness matrix. Okay. Now, the measurement equation, what it does is to relate these 2 matrices, relate what we measure with what we want to have, okay? And this is the equation. This is the famous and very important radio interferometer measurement equation. As you can see here, the brightness matrix is here. This omega is just the angle, the solid angle on the sky, okay? So we are integrating over the whole extent of the source. The brightness matrix, so this is the integral of a matrix, okay? Pay attention. And here we have a kernel that many of you will recognize as the Fourier transform kernel, okay? Computed at the point in Fourier space given by the baseline, which is this B here, is the vector joining the 2 antennas, okay? So this is the Fourier transform of the brightness matrix, okay? Beware, the Fourier transform of a matrix, okay? Evaluated in the point of Fourier space given by the baseline, okay? This Fourier relation would be pure. This would be the pure Fourier transform of the visibility if we wouldn't have these 2 red things here. These are the problems and headaches of all radio astronomers in the world, okay? These J matrices here. If they wouldn't exist, then we would have a pure Fourier relationship between the visibility matrix and the brightness matrix. But that's not the case, okay? We have these 2 matrices that depends on antenna A and B, and we call calibration matrices, okay? These calibration matrices must be known so that we can apply them to the visibility matrix and then get the Fourier transform of the brightness, then have a pure Fourier relationship, okay? Here I give you some examples of these gain matrices that we need to find, okay, from our observations. For instance, the gain matrix, which is basically, yeah, the amplitude and phase gain or the atmospheric contribution as well. Delay gain, I'm not going to talk about this, okay? I will just go through. And the bandpass, which depends on frequency, I'm not going to talk about it either. One important point here, actually, is that as you may have noticed, all these matrices are diagonal, okay? We have zeros here. If they are diagonal, it means that we can multiply them with any order we like, okay? They commute among themselves. But in general, J matrices may not be diagonal. So that means that the order matters. And this is, I tell you, this is a real headache for the radio astronomers to know what is the exact order of application of the calibration matrices when they do not commute, okay? So what I'm going to show you here is the measurement equation graphically, okay? So we are going to see graphically what's happening. But just for a Stokes eye, okay? This is just a very graphical and easy description of what interferometry is doing, okay? And just for a Stokes eye, okay? Remember this. What I'm showing you here is an image that you are observing with an interferometer. This is a very beautiful image, okay, in the sky. Then we are going to observe it with telescopes that I'm going to place here, okay, in this map. This is the Fourier transform of this source, okay? So this red thing here is the Fourier transform of the image. And as you may remember, what we are going to do when we observe with an interferometer is to take samples of the Fourier transforms in the points given by the baselines, okay? Then if we take these samples and we Fourier transform them back to the image space, we will have the reconstructed image, okay? So let's start with 2 antennas. I place 2 antennas here, one in Madrid to another one in Onsala, and then we only have 2 points in Fourier space. If you take these 2 points and you transform them back to the image space, you have a plane wave. Well, a plane wave doesn't seem very similar to the source, isn't it? It's a very poor representation of the source. Let's add more antennas. Let's add another antenna. When you have another antenna, you have 3 baselines. You have 3 combinations of pairs of antennas. Each one of these combinations will introduce a different plane wave with a different spatial frequency, a different direction, a different phase, a different amplitude. And all these plane waves will add up to each other coherently in the image plane, and they will try to reconstruct. As you add more and more antennas, all these plane waves will interact, it will interfere with each other, and will slowly and steadily reconstruct the image, okay? You can go even to transatlantic distances, okay? And as you can see, well, maybe some of you will see the hint of hello here. Yeah, do you see it? Yeah, you need a bit of imagination. But now is where the magic comes, okay? Now is where the magic comes. Now, what I'm going to do is to let the Earth rotate. If you let the Earth rotate, then the baselines, as seen by the source, will start rotating as well, okay, as they are seen from the source. And this will allow us to sample different points in Fourier space, to rotate these samples, okay, and then take more and more and more measurements of the Fourier transform of the source in different points, okay, of Fourier space. And then the transform, as you will see, will improve a lot. This is magic. I love this animation, okay. Here you see how the Earth rotation, what we call Earth rotation synthesis or Earth rotation aperture synthesis, allow us to actually make a very, very high fidelity reconstruction of the observed sources, okay? This is what we have with Earth rotation. But this is a Stokes eye, okay? So don't forget, this is just for a Stokes eye. What happens when you have the 4 Stokes parameters? Okay, when you have the 4 Stokes parameters, you don't have the mere Fourier transform of a scalar quantity that I'm showing here. You just have one scalar, a Stokes eye. No, you have a matrix, okay? So you are Fourier transforming a matrix, okay? And from this matrix, you have to decouple the different Stokes parameters and recover the brightness distributions of the 4 Stokes parameters, okay? For doing that, we also need Earth rotation. But the reason why we need Earth rotation for polarimetry is a little bit different, okay? We need a rotation for a different reason. The reason is that, as you can see here, when the Earth rotates, the polarizers of the antennas, whose orientation is shown by this green arrow here, green mark here, they are tied to the Earth, isn't it? Because the antennas are tied to the Earth. So the orientation of the dipoles follows the Earth, doesn't follow the sky, okay? Whereas the source is tied to the sky and it rotates with the sky, okay? This angle between the axis of the antenna mounts and the source, what we also call in our jargon parallactic angle, okay, is actually what is introducing is actually this thing in the image plane, okay? What it does is acting as a rotating polarizer. So if the source, if this yellow square here is this square here, you can see that the Earth rotation is causing the polarizers of the antennas to rotate with respect to the source. And since any instrumental polarization is tied to the polarizers, whereas any effect due to the source is tied to the source, then the Earth rotation allows us to decouple instrumental effects from source intrinsic effects. And by using this, by using the Earth rotation, we can disentangle what is instrumental and what is intrinsic to the source. In order to apply these matrices of calibration, find out these calibration matrices and apply them to the visibility, okay? So in the case of polarization calibration, we have these matrices, okay? Most of them are diagonal, as you can see, okay? So they commute among themselves, is wonderful. But there is one here, which I tell you, it's the biggest nightmare of any radio astronomer dedicated to polarimetry, which is not diagonal, okay? And hence it doesn't commute with the rest of the calibration matrices. So it is very important when you apply it, okay? And that introduces a lot of limitations, a lot of problems in the calibratability of the data, okay? This is very, very troublesome. Okay, you have to take a lot of care to do it properly. This matrix is what we call D-term matrix, and the D-terms, which are these quantities here that may depend on frequency, as you see here, are typically caused by the crosstalk between the polarizers. Okay, as you already know, or you may already know, something that is receiving a signal, a receiver, okay, is also a transmitter. Any receiver has something of a transmitter in itself. Okay, so it receives signal, but it also re-emits the signal. And this re-emitted signal can be received by the other receiver. So you have a kind of a crosstalk or mix of the signal between the two polarizers. You can also have cases where the polarizers are not perfect and they are not exactly orthogonal. They are not exactly at 90 degrees. They may be at 89.5 degrees, okay? And all these imperfections in the design of the receivers would introduce this crosstalk between polarizers. So if you remember the measurement equation, what this matrix does, if you have the visibility matrix here, is basically assigned to right-right, a linear combination of right-right plus something a little bit of right-left. And the same thing for left-left, which introduces us something a little bit of left-right. Okay, so this mixes, blends different components of the visibility matrix. Okay, as I tell you, this is a very dangerous matrix. And this is especially dangerous, even more dangerous for the case of VLBI, okay? Because in VLBI, we have a very large aperture, we have very high resolution, and that means that almost all calibration sources, almost all sources that we should describe are resolved, have resolved the structures, okay? They are not points, okay? The fact that they are not points complicates a lot the brightness matrix. The brightness matrix is not just a simple constant, okay, which is the Fourier transform of a point, as you may know, okay? It's a complex valued, complicated thing, okay? In case of these complex brightness matrices, what we need to do in VLBI is to solve them at the same time as the determined matrix, okay? This is very, very troublesome, okay? Because each one of these matrices appears in a different side of the measurement equation, okay? And the fact that we need to know them both at the same time, okay, is complicating a bit the things, okay? So that until a very little ago, there was only one code in the whole world able to do this, able to calibrate VLBI polarimetry. It is this software here called LPCal. Okay, LPCal was the only software in the world which was able to do this kind of complex mathematics that allow us to decouple brightness matrices from determined matrices by solving them at the same time. Okay, but now in the frame of the Event Horizon Telescope collaboration, we have been dealing a lot with this kind of problems, as you may imagine. And actually, as you can see in these dates here, it's pretty, well, it's pretty new. Everything here is pretty new. We have a little bit more fauna of algorithms able to do VLBI polarimetry. Okay, we have GPCal, which is based on the same software as LPCal, but has some improvements with respect to LPCal. We also have PolSolve based on CASA, which is a newer infrastructure for the calibration of interferometric observations. All of them, all these three, are based on the same philosophy, what we call inverse modeling, okay, which is basically retrieving the image, retrieving the model from the data, okay? Whereas here we have forward modeling philosophy, which actually tests the models from the data, okay? Which is a little bit different philosophy, as you may imagine. We also have Markov chain Monte Carlo samplers, okay, which actually probe everything, okay? They recover the posterior distribution of the instrumental polarization and the source structure at the same time. It's very powerful approach, okay? But each one of these software has its own advantages and disadvantages, and you may imagine. And well, I would have liked to talk in a bit more detail about all of this, but I'm really running short in time. Actually, I've been running a lot. I hope you have understood the most important slides, because this is the end, I'm afraid. So in summary, I hope you have, I hope I have transmitted you the mantras, the most important mantras of this polarization seminar. Okay, we have reviewed the basic concepts of polarization, modes of polarization, linear and circular, and Stokes parameters. Beware that for us astronomers, the convention to define Stokes parameters is different from what you find in most optics books, okay? So take a lot of care with that. We have discussed about the origin of polarization in the universe, okay? Absorption and emission of dust grains immersed in magnetic fields, and also synchrotron emission, okay? And we have also discussed about the different, oh, sorry, that's my R2D2. And telling me that I'm running out of time. So we have discussed about the different kinds of polarizers in the radio astronomical receivers, the linear polarizers and circular polarizers. Remember, these are coherent polarizers. That's why we can reconstruct 4 Stokes parameters with just 2 polarizers, okay? Because we have the phase between them, okay? The fact that they are coherent allow us to reconstruct everything from just 2 polarizers. And we have studied how to deal with polarization in interferometric observations. I gave you a very, maybe too brief introduction to the measurement equation and the concept of aperture synthesis and interferometry. I've briefly introduced you the matrices for polarization calibration and told you about what we call polarization synthesis, okay? The fact of using polarization, Earth rotation to decouple the instrumental effects from the source intrinsic effects. And I also told you very briefly as well about the tricky polarimetry calibration in VLBI and the available software that we now have to perform these calibrations. So please don't forget to give feedback, okay? To give feedback about the seminar, okay? And thank you, all of you, big thanks for all of you for listening. I'm ready for questions. Thank you.
Okay. Thank you very much, Iván. That was wonderful. So let me second the comment that Iván made, that it would be great if people could spend the sort of 30 seconds filling out feedback between now and the hour. We did have one question already from Ruben Valerio, who asked, how strong do the magnetic moments of dust have to be to make a considerable distortion of an image?
Wow, that's a very good question. Actually, they are important, but they may not be as important as the magnetic field. Okay, so since the dust density is so low that you basically don't have collisions among dust grains. Okay, so you don't have thermal equilibrium there because there are no collisions. Each dust grain is completely free to rotate without interaction with the others. Okay, there are very little interactions. Okay, so that means that if you have a magnetic field which is strong enough, just having a dust particle that is a little bit elongated would already introduce some polarization. Okay, I don't have the numbers. Sorry, I don't have the numbers. But qualitatively speaking, okay, since the dust densities are not that large, I mean, in normal circumstances, okay, then basically, yeah, you will have polarization as soon as you have some ellipticity.
Okay, do we have any other questions, either in the Q&A or the chat? Someone has their hand up. I'm sorry. Whoever that, oh, this is Johannes. I'm not sure whether you can speak up or not. Can you go ahead and speak? Yes, Dimitris.
Hello.
You can, yeah.
Yes. Hello, thanks. My question is, I liked very much the multiplication of the baselines when we have the Earth rotation. So my question is, in Stokes Q and U, does the parallactic rotation of the source actually multiply the available baselines in Q and U, so we can have even better coverage of the plane, of the UV plane in Q and U?
That's a very good question. Very good question. Actually, in Q and U, what you have here, well, let me go to the measurement equation. Go back here. In Q and U, you have here for the parallel, the diagonal elements of the brightness matrix are linear combinations of I and V, whereas the diagonal elements, the non-diagonal elements of the brightness matrix are two combinations of Q and U, which means basically that you have 2 degrees of freedom in each thing, okay, and then you have 2 quantities. So in principle, you have the same UV coverage for all 4 Stokes parameters, I, Q, U, and V, okay? But beware that there are some peculiarities of Q and U, okay, that are maybe too detailed to be described here, which is the fact that you may not have an Hermitian brightness distribution because this is complex, okay? So yeah, in case of Q and U, you can have some subtleties there, but in essence, you have the same UV coverage because you have the same amount of degrees of freedom and information, both for IV and QU. Did I answer your question? So no, yes. Regarding the Earth rotation, of course, when the Earth rotates, this is Q and U measured on the sky, okay? This is Q and U measured on the sky. But the antennas are rotating with respect to the sky. So the Q and U that the antennas see, okay, are affected by the parallactic angle, which is one of the J matrices that have to be applied here. I don't know if this goes more in line of what you were asking. So you have to undo the parallactic angle to bring the B matrix and the V matrix to the same frame, okay? Because these 2 frames are rotated. The visibility matrix frame and the brightness matrix frame, they are rotated by the parallactic angle. You have to put them in the same frame. And this is one of the J matrices here. Did I answer?
My question? Yes, yes. My question was actually if the rotation of the parallactic angle actually improves the situation for Q and U imaging, or you know.
What it improves is our ability to disentangle what is instrumental, because the D matrix, the D term matrix, is tied to this frame, the frame of the antennas. Okay, and the QU matrix is tied to this frame. So the D terms and the brightness matrix are in different frames. So the changes in parallactic angles allow us to decouple one from the other, because one is rotating with respect to the other. So what the rotation helps us to do in polarimetry is to disentangle what is source and what is instrument. Okay, this is what allows us to do the rotation for polarimetry. But the baseline, or the coordinates in Fourier space, are exactly the same for all four.
Okay, thank you. Thank you.
Thank you to you.
That answers.
Okay, so Yifan has a question. Can we open up his mic as well?
Hi, can you hear me?
Yeah, go ahead. Yes.
I want to ask you a question is, what determines the uncertainty of the EVPA, and how to improve it, for the NG-EHT? So will you more coverage improve the uncertainty of the EVPA or not? Oh,
that's a very good question. Actually, if we come back to this animation here, the previous one, okay, so the EHT and the new generation EHT, all of them, okay, will register the radiation in circular basis. Okay, so we are going to record RCP, or right circular and left circular polarization. As you can see, the EVPA, the orientation, is basically given by the phase between the two polarizers. So that means that any instrumental effect that adds a phase between the two polarizers, and you have many effects that can do that, okay, because the optics is not exactly the same. The waveguides are not exactly the same. You have different cable lengths, for instance, okay? So you have many instrumental effects that can introduce offsets in the phase between right and left, which means that the precision you have for the EVPA determination is very poor in VLBI. This has been a problem for years, for many years in VLBI. But the EHT is a special telescope, okay, because it has one element called ALMA, okay, Atacama Large Millimeter Array, that registers the radiation in linear polarization. So what we have in the EHT is a combination. One of the elements of the EHT, which is ALMA, is registering the radiation in a different basis as the rest of the EHT, okay? The fact that we are registering the same wavefront, the wavefront that comes from the black hole, in two different bases of polarization allows us, if you do the math, you will see, allows us to decouple the absolute EVPA in a way which is independent of any instrumental effect. It's like magic, okay? So the fact that we have a linear polarizers in the EHT allows us to register the EVPA with a very high accuracy. What's the limit then? What's what dominates the error budget of the EVPA in the EHT? So basically, the precision in which the receivers of ALMA are built, basically, okay? The fact that the antenna axes are not exactly horizontal, because the antennas are not exactly, well, calibrated on the ground, let's see, they are not exactly horizontal, okay? And the receivers are not exactly at 10, 45, or 60 degrees, wherever they are built, okay? We have maybe offsets of half a degree or 1 degree, okay? So the error budget would be dominated by that, by the actual construction of the receivers. But there is nothing in the instrumental gains that will introduce errors in the EVPA for the EHT. We are lucky to have at least one antenna with linear polarizers. Did it answer your question?
Yes, and I want to ask, so was this like how much percentage of this resolution be improved further in the future or not? If we had like more linear.
Well, that's a good question. Thank you. Because I'm talking about the precision in the absolute EVPA, but of course, on top of that, you also have the thermal noise. Okay, because what you register, of course, there is thermal noise here being added to the measurement equation. Okay, there is noise here, and this noise here translates in noise here. So you have noise in all Stokes parameters. You don't have a perfect determination of them. You always have a delta in Q and a delta in U, which is noise. Okay, so noise here, of course, translates into an uncertainty in the polarization intensity and also in the EVPA. Okay, because they are tangent of U over Q. If you have an error in U or Q, then you're introducing an uncertainty in the EVPA. So that means that we are also limited by thermal noise, okay, or by sensitivity, which means that having more antennas and having better receivers and wider bandwidths would allow us to have more signal to noise and hence have a more precise determination of the EVPA.
I see. And about the D-term leakage, is that the dominant noise or not?
Oh, not exactly. Actually,
okay.
One of the things we have learned from the ipht data processing is that we are actually limited more by dynamic range. Okay, so one of the limitations that you have in interferometry is the fact that you are not sampling the Fourier space in all space. Okay, you are only sampling the Fourier transform at the points given by the baseline. So you have huge holes in Fourier space. Okay, these holes in Fourier space introduce dynamic range limitation, which is like limitation in the contrast, okay, and limitation in the fidelity of the image reconstruction, okay? So depending on the particularities of the methods of the algorithms that you use to reconstruct the brightness distribution from the visibilities, you may have a slightly different models, okay? This is what we call in our jargon fidelity limitation, okay? And also dynamic range limitation, okay? So what we have learned from the analysis of the ipht data is that actually our precision to determine the D terms is actually better, much better than the limitations or the effects of the residuals of that calibration is smaller, actually quite smaller than the uncertainty that we have because of the fidelity limitation produced by the holes in UV space. So we have a very good determination of instrumental polarization.
I see. Okay, thank you very much.
Okay, thank you. We have a number of questions in the Q&A, but before we go to those, I just want to remind people to fill out the feedback link that Rosie put in the chat, and also that there will be a YT workshop sponsored by PIRE happening this Friday, and I just put the link to that back in the chat. So Milan asks, do you think we can combine data from telescopes on Earth with data from telescopes on the moon in the future?
Wow. Yes, we can. The problem is money. So in principle, VLBI allows you to basically generate any baseline. Okay, because VLBI is basically recording the signals. So you are not computing these correlations in real time. You are recording the data in disks, and these interferences, these correlations are like frozen in time, okay, waiting to be generated in a computer. Okay, so the interferences that we build in VLBI are frozen in time, are not computed in real time. They are frozen. Okay, they are waiting there in a kind of limbo to be processed in the correlator. Okay. This means that it doesn't matter how far these two antennas are, as long as they record the signals and we have enough precision to model the time evolution of the signals and recover the front wave of the original radiation that came to the antennas. As long as we can do that, we can build an interferometer of any size, even the size of the solar system, if we have enough computing power and enough money. Okay. The problem is which source would we observe with such long baselines, but it can be done.
And a question from Andreas, which I believe is, how do you deal with position angle correction in mixed arrays with linear and circular feeds?
So what you do basically is to use a software, okay, called PolConvert, which is being used by the ipht to treat the signals coming from ALMA, okay? And once you do that, a byproduct of this polarization conversion or PolConversion, a byproduct of that is that the right-left phase of the antennas that originally had linear polarizers, that phase is 0. By construction is 0. So that means that if you use these antennas as reference antennas, okay, to measure the phase of all polarizations at all the other antennas, so this is like your clock standard, you define that antenna to be your clock, okay, then the fact that the relative phase between right and left is 0 allows you to recover automatically the absolute EVPA. So the only thing you have to do is to use the antenna that originally had linear polarizer, to use it as your reference, okay, as the reference to determine the phases of all the other antennas. By doing that, by construction, the data that you will have will be calibrated in absolute EVPA. Okay,
Thank you. So again, before people go, we're at the hour. Please fill out the short survey. We do have a few more questions, and Iván has kindly agreed to stay on and answer them.
Yeah, no problem.
So an anonymous attendee asks, for non-astronomers, what would be a good place to start learning about more about polarimetry?
Wow, what a question. Well, there is a lot to look at, but you mean polarimetry in general, or polarimetry in radio astronomy?
I'm guessing it's polarimetry in radio astronomy.
Okay, well, I would suggest then to start with the Thomson, Moran, Swenson. Yeah, you know, this is like the Bible of radio astronomy, which has very beautiful chapters about polarimetry and basic ones, and then from that start growing. Yeah, but I would suggest to start with very basics. And actually, I think that the chapter that talks about polarimetry is very beautiful. I like it. And there are, of course, other publications. For instance, there is a very nice set of papers by Oleg Smirnov in 2011. It's 6 papers, actually, if I remember well, which treats all the peculiarities and particularities of the measurement equation, from the very basic definitions till the very, very elaborated calibration strategies. So this is a set of 6 papers, okay, Smirnov, 2011, that actually gives you a very nice introduction to the measurement equation, and it starts with an introduction, and then it keeps complicating things until the very end of the last paper, which discusses even direction-dependent effects and all kind of funny things that fortunately don't have any effect on VLBI.
Okay, thank you, Iván. Renee asks, is it understood that we can measure the magnetic field direction from polarization, but can we also measure its strength? And that is not a basic question. That is a very good question. So Iván,
yeah, that's too good. That's too good. Because it depends on many things. It depends on many things. Okay, there are some tricks. Okay, for instance, you can use a spectropolarimetry. If you have spectral lines immersed in a magnetic field, you can use spectropolarimetry to derive the component of the magnetic field parallel to the parallel to the line of sight using some quantum effects. There are also other effects that allow you to infer the components of the magnetic fields parallel to the sky plane, okay, by using, for instance, how was it called? This Chandra Fermi method in turbulent plasma, for instance. There are more direct and more indirect ways, but there are different options, okay? Of course, you cannot use them always, okay? So each scenario, so each method can only work in a different specific set of scenarios. But in general, what I would say is that all these methods are model dependent. Okay, so you need to have very good and realistic models of your source if you want to retrieve from the observations in an accurate way the strength of the magnetic field. So, for instance, one of the ways, which is the one that I most use, is to use Faraday rotation. Okay, so if you can infer how the EVPA changes with frequency or with wavelength, you can relate this to what we call the Faraday effect, which is the fact that a birefringent magnetized plasma, which is a plasma basically immersed in a magnetic field, induces different phase speeds for right circular and left circular polarization. And this, what it causes is a rotation of the EVPA. Okay, and from this rotation, you can infer the strength of the magnetic field, with the drawback that you infer it coupled to the density of the magnetized plasma. Okay, and it's very tricky to decouple one thing from the other. It's very tricky. So this is a very good question. And I'm afraid I don't have the full answer to that.
Yeah. Okay, thank you. So Guillermo asks, is there a criterion for selecting the integration time for each VLBI station as compared to a single dish observation?
Wow, this is very good as well. Yes, well, you are limited by two things. So on the one hand, you need to have an integration time long enough to detect the interference fringe. Okay, this depends, because the signal to noise ratio of your fringes depend on the source structure and depend on the baseline. Okay, because what you are registering is a sample of the Fourier transform, okay, of the source. So if you are unlucky and your baseline is close to a null in the Fourier transform, then you need a lot of integration time to detect the fringe. On the other hand, you have, which is also important in VLBI, especially important in VLBI, is the coherence time of the atmosphere, okay, which goes the other way around. It's very short, okay? So you need your integration time to be short enough to not kill the interference because of the coherence time of the atmosphere, and you need to be it to be long enough to detect the fringe. So it's a compromise, okay? If your integration time is too long, you will kill the interference, you will kill the fringe, because the atmosphere is not the same. Okay, one antenna is in summer, the other one is in winter at the other side of the Earth, and it's very difficult to have the same atmosphere. Okay, that means that you have very different coherence times and very different weather conditions. Sorry, and the coherence time may be a big problem. Okay, the fortune that we have with the ipht is that we have stations that are very powerful, very sensitive. I'm thinking of ALMA, okay? ALMA is by far the most sensitive element of the array. And that means that all baselines related to ALMA, since ALMA is so powerful, so sensitive, all baselines related to ALMA detect fringes in just a few seconds of integration, okay? It's fantastic. We see signals after just a very, very short integration time for all baselines related to ALMA. And we can use this to correct the atmosphere in all stations, atmosphere relative to that of ALMA, of course. And then we can use these corrections to make our integration time longer for all the other baselines and detect the fringes. So this is a very, very smart way of proceeding, isn't it? So we use the most powerful station to allow us resolve the fast atmospheric changes. And once we know this, we can then increase the integration time to allow the less sensitive baselines to detect the signals. I don't know if I answered your question.
Guillermo says yes. All right. I think that brings us to the end. We don't have any more questions. So I want to thank Iván again for a brilliant presentation and for answering everyone's questions. And again, we'd like people to answer the short survey, take about 30 seconds, and have a look at the PIRE website to see what webinars are available in the future, and especially if you're interested, the seminar on the workshop on YT this Friday. Okay, thank you.
Thank you very much.
Bye.